cool. Okay, hi everyone. So today I would like to briefly talk about how we can actually use Simple for creating photorealistic and controllable neural avatars. And part of the work that I'll be discussing was the joint work with Michael and Javier Romero during my internship at Amazon. Okay, so first I would like to outline two main goals of this tutorial, which is, first of all, I would like to briefly discuss current progress and limitations in both neural rendering and classic computer graphics when it comes to modeling humans and rendering them realistically. And then I would show some of the recent work from our group and some of the latest CVPR works, which also use simple models as kind of a solution and a proxy for neural rendering. So more specifically, this means the following outline. So we will start with discussing our goal of robust and controllable neural avatars. Why would we need that? Then I would give some intuition about state of things in computer graphics and deep learning. And then I would discuss SMPLpix, which is the model that we propose for creating neural avatars based on Simple and SMPLx models. And I would also then discuss some of the latest developments in terms of the code we released that will allow you to actually get the neural avatar of yourself, for example, from just a phone video. And then I will briefly mention some of the latest work that combines Simple and, for example, recently developed neural radiance field. And hopefully we'll have some time for questions at the end. Okay, so let's start with the goal. Our goal is to create something like the image on the left, which is from this project Samsung Neon. And the idea is that we want avatars that looks just like humans and moreover, which we can control and put, for example, into 3D scenes realistically, which means that we would need to accommodate for novel pose change, light effects. We'd also need to understand how to place them coherently in the environments. And of course, these have enormous potential in things like virtual reality, augmented reality, completely novel ways to do computer graphics, teleconferencing, and also synthetic datasets, for example. And I would like to start maybe to showing like what current classic computer graphics can get us to. And here you see some of the latest demos from Unreal Engine 5. And just from looking at it, you can see that, first of all, there are, of course, two main advantages of classic mesh-based rendering, which is, as you see, you have a full control over scene. So you can change the light, you can manipulate character in a nice way. And another nice thing that actually the whole pipeline is very robust to novel views and changes in the light. So it's really simply independent. But at the same time, if you start to look for like high frequency details, you can see that there is this classic uncanny valley of realism. And for example, when it comes to modeling hair or clothing and also like dynamics of human motion, and even like with the latest sophisticated semi-manually created avatars, such as, for example, these metahumans that you see on the bottom right, they don't quite get us the same level of realism as we would observe in the natural photos. Okay, if we at the same time consider latest developments in neural rendering, such as, for example, neural radiance fields or StyleGAN, or this latest neural lumigraph, you can see immediately that the advantage that we get is the high degree of realism. But at the same time, at least currently, what we pay for it is like regularly we have a very limited control over camera pose, and so the quality will deteriorate significantly as we generate the views that are far away from the training data. And the same goes to reposing the avatars and overall controllability for some of these models. So the question is then, of course, how we can combine the strong sides of both worlds, right? And one of the approaches that I would like to discuss today is obviously based on Simple. And the idea is that on one side, we can use these deformable 3D models, and in particular simple, but we can also use flame, like space-specific model, or even animal models. And in this particular line of work, we'll be combining them with this famous pix-to-pix style image-to-image translation networks. And here, I would like to just introduce our approach to tackle this problem. And the idea here that we start with simple vertices, and we will get for them RGB colors also, and which we get from the alignments to the 3D scans that we had back then at Amazon. So imagine that what you have basically is this V template simple model. So you get the per vertex colors as just stealing it from the scanner data. And yeah, and also of course, since it's a restricted camera scanner setup, you also have the ground truth camera parameters for your model, for your scan. And the idea is what we have then is a nice way to control these vertices via pose and shape space of simple. And what we do then is that using this this alignment and the camera model, we will project it into the image plane using the camera parameters, and we'll get this RGBD image of the projected vertices. And then what we're going to do next is we're going to use some neural network. In this particular case, we use a variant of the UNet network to generate something that we'll then train in order to in order to minimize a combination of perceptual and GAN-based loss with the ground truth image. And the ground truth image we have because we basically have this segmented out image from the scanner. Okay, and maybe to just showcase it in a more clear way. So what you see on the right and on the center is two inputs to the network, and what is being generated you can see on the right. So sorry, so the left and center are the inputs, and right is the output. And to train this thing, we of course need enormous amount of data, and this. And what we use basically is 1,600 different subjects. And for them to train it, we need more than 100 camera views, of course, ground truth camera parameters and simple alignments. And then we test it on 68 novel subjects. So just to mention, so in comparison to many other works, so here is it's the same neural network that works for all the subjects, including unseen subjects during the test time. And all the examples I'm showing here are the test subjects. Okay, so one of the things to when it comes to qualitative comparison, for example, classic mesh-based rendering, is what we see here is like the classic mesh-based rendering will give us these artifacts around, for example, long hair, because obviously we cannot represent it with simple model, even if we use vertex displacements. And these things we can then fix nicely with the neural rendering. And the same goes, for example, for these artifacts in textures. So for example, here you can see that hands sometimes have these like leaking pixels from the background that are being assigned to hands. And this is also nicely fixed by the neural rendering approach. Those are just a few more examples. For example, you can see the improved hair region and also feet region that are being translated from this simple toes to something that looks more like shoes. Also, quantitatively, we show that both in terms of PSNR and perceptual similarity scores compared to just classic texture-based mesh rendering, we get improvement in terms of both metrics. And then I would just like to show more of the qualitative results. For example, here we can just generate novel views across cameras, and you can see that they're mostly consistent across views. I mean, there is, of course, some flickering happening. And another nice thing which we get by using a simple as the proxy, is that basically by modifying betas of the simple model, we can also change the appearance of the subject. For example, here we change one of the first few PCA components, and we can see that subject becomes thinner or thicker depending on where we move the slider. Another interesting thing is that we can also use MS repository of motion capture, and we can repose all the avatars with the same motion sequence. There's just some more examples of that. Okay, so but this is of course was all like with the proprietary data. So you need to get quite a lot of the scanner data to train this model, and what we actually provide publicly available for public is the model that you can train on your video input. And here, for example, we show this kind of video data that you can capture at home yourself, and with the simple mobile phone. And here, like the video is being segmented with either like the some of the services available online, and you can use point trend framework for this. And the idea is that in this case, of course, we don't have proper scan, like 3D scan, but what we do here in order to get a simple model, we basically follow SMPLpix approach. So for every frame, we'll get the open pose 2D key points, which we then use to estimate SMPLx model based on the SMPLpix framework. So, and then what we basically get for the training is as input, we will get the SMPLx mesh with the pose being inferred with SMPLpix. And here, since it's the per subject model, we're going to use actually some fixed vertex colors, which is this rainbow coloring. And we will use the same UNet type of neural rendering to get the neural avatar, which we will compare with the ground truth imagery. And here we just use the VGG laws because we figured out that for this specific single subject case, we actually don't need to go for the GAN-based part. And here you can see the results for the test sequence. And on the center, you can see the neural render, and on the rightmost, you can see the ground truth image for the for this test sequence. And overall, of course, you can see some flickering due to SMPLx estimates made by SMPLpix, but overall, I would say that the results look quite decent in terms of photorealism. Another thing is that, of course, you can use it in the same way, not for the full body, but also for detailed modeling of faces only. And here, for example, we show how you can estimate like the same way we've done it with for SMPLx with SMPLpix. We use the recently proposed DECA framework and estimate textured flame model, and in the very same way, we then use it to generate these face renders. And you can see that hairs are also modeled quite nicely, and yeah, and facial expressions are mostly preserved for this test sequence. And finally, like another fun application that you can also use it for some kind of artist style transfer. And here we just use very few artist created sketches, and then basically we used some augmentation for these 18 training examples that are available. And so this allowed us to generate this kind of artistic stylized animation sequence. And again, we use the MS motion sequence to drive the animation. So here is just a small example. Okay, so I would like to conclude with briefly mentioning a few other works that also use simple for neural rendering. For example, this year CVPR, there is a work that combines simple and neural radiance fields. And very roughly, the idea is that instead of using just vertex colors, here what is used is some learnable latent codes that are attached to every vertex of a simple model. And then those Latin codes are used to translate it to some neural volume that is like in the NER style is being used to get the density and color information for every ray of interest and to generate this photorealistic imagery that you can see on the bottom right, or on the top right, sorry. Another work is neural body, which again, and here again, the approach is somehow similar. Maybe one of the interesting things is that they also use the available ground truth texture map supervision to drive this NER style training. And compared to the previously mentioned work, it seems that they are a bit more robust when it comes to actually reposing subjects, even for the poses that have not been seen during training. So overall, I would say that results look quite decent. Okay, and this is also like some of the references that both mentioned and not mentioned in this talk. So, and I'm sure that this list is far from complete, but this is just to get you an idea that nowadays there is a lot of work on this intersection between simple and neural rendering that's being done. So I would like to conclude now with just maybe outlining some of the take-home messages, which is like the first one is that obviously like the classic computer graphics approach have certain strong advantages, which is like robustness and controllability. But we can definitely explore neural models to basically traverse this final uncanny valley of realism. And in that sense, Simple, in my personal opinion, provides great capabilities as the backbone for neural rendering. And I'm sure that in the years to come, we will see a lot of more things in this intersection between Simple and NER style, also including modeling light, some fine geometry modeling, etc., etc. So with this, I would like to conclude my talk. And so the code for the mentioned part is actually available online now with some collab tutorials to get you started. And I'm happy to take questions now.
Thank you, Sergey, very much for the amazing talk and the great results. Are there any questions? So there is a question in the chat. In all the examples you gave, the neural render is specific to one person, or is it possible for it to generalize to multiple subjects?
Okay, yeah, so there are basically two models that were shown. So the first one, which uses this proprietary Amazon data, is actually multi-subject data. So, and it basically, it's the one render that is used for all the subjects. So it's a multi-subject data. But the second one, which is publicly available, is only trained on a single subject. But if you have the data that it takes, basically, that there's nothing that stops you from training a multi-subject model for that. Yeah, hope that answered the question.
Okay, and then there's another question. How photorealistic do synthetic human avatars need to be in order to train robust real-world models? Is the uncanny valley you mentioned from MetaHuman a problem?
That's a very good question, and I think the thing that is to be explored in the future, and I guess for some of the things, and I think there was already some works from Microsoft showing that if we are, for example, interested in generating data for human pose estimation, I guess this gap might be small enough to actually this data to be useful, like even in terms of meta-humans and things like that. But I don't know, maybe for more sophisticated things like autonomous driving cases, I don't know, detecting pedestrians, that's the thing to explore. So I would say like there are lots of applications and types of synthetic data sets that you may need. And for some of them, I'm sure that even these meta-humans would already serve nicely. But yeah, I mean, in this particular case, it's a thing to explore. Yeah.
Okay, the last question is, what is the quality with the new pose for new poses or new camera view for the iPhone captured video case?
Okay, yeah. So basically the idea is that, of course, if you don't capture if you have the fixed camera, of course, you won't go very far with generalizing to novel camera. So you basically need more, you also need the camera to be moving. and then you can hope and you can actually get some generalization. But of course, since it's this kind of pix-to-pix based model, don't expect it to work super nicely on some extreme novel camera views. And this is actually one of the open problems, I think, to be addressed.
Body poses, body poses as well, new poses and new camera views.
I mean, yeah, so for the body pose, it's always about, how different is the body pose from the training set. If it's something that is, I don't know, some yoga pose, which is completely unseen during training, I would expect it to fail, actually. So, yeah.
Super.
Thanks.
Thank you.
We should move on because we're now a couple minutes behind schedule. So just for the speakers, if you can leave space for questions, that would be awesome.
Yeah. So thank you, Sergey. And